Hello everyone, my name is Dirk from the Bekerom and I'm a postdoc at the Combustion Research Facility at Sandia National Labs in Livermore. The work I will be presenting today is work I did at Ohio State University, where I worked on a new approach for spectral synthesis that can synthesize spectra very fast while still maintaining accuracy. Here's the outline of today's talk. After a general introduction, I will quickly review the conventional synthesis method that is mostly used today. Then I will go into the details of our new method and present benchmarks comparing the new method with the old one, where we find that the new method shows a 2 to 3 orders of magnitude improvement in performance. After that, I will briefly talk about an experimental GPU implementation with which we were able to achieve an additional 2 orders of magnitude improvement. Finally, I will finish off with some concluding remarks. My talk today is about the synthesis of spectra from large line-by-line databases. Line-by-line databases are used in a number of applications, such as tabulating cross-sections, opacities, and extinction coefficients. They're used for deriving approximate models such as SMB and CK band models, and they can be used in direct comparison with experimental data such as fitting spectra of high temperature combustion or laboratory plasmas. It's important to be able to synthesize high accuracy spectra, which are required for more accurate radiative transfer modeling, such as in combustion and heat transfer, but also to prepare for new high resolution instruments such as the James Webb Space Telescope. And the problem generally is that for a higher accuracy, you need to include more lines in the spectrum. And this is nicely illustrated in the graph on the right here, which shows the number of lines needed for 99% accumulated line strength. And at 300 Kelvin, this is only 180 lines, whereas at 1000 Kelvin, it's already 13,000. And at 3500 Kelvin, it's already 2.6 million. And this shows the need for a spectral synthesis algorithm that can process these large number of lines efficiently. A spectrum is usually synthesized by taking the input parameters such as temperature, pressure, and mole fractions to process a line-by-line database that outputs the line position, line strength, Gaussian width, and Lorentzian width for each spectral line. These 4 parameters per line are then used to produce a broadened output spectrum. This second broadening step is almost always the bottleneck, and this is where our approach focuses on. In the conventional method, the output spectrum is generated by iterating over the spectral lines in the line list and calculating a Voigt profile for each line. All these profiles are then added together to get the output spectrum. Because in this method we produce a line profile for every line, the computation time scales with the number of spectral lines times the number of spectral points. This is a problem for large databases, as the computation time will increase and increase as we include more lines. Line profiles are often truncated to improve performance, but this is at the cost of the accuracy of the output spectrum. A more substantial improvement could be obtained when the line profile is constant for every line, as the broadening would only have to be applied once. If, hypothetically, the line shape was constant for all lines in the line list, we could efficiently calculate the output spectrum as the convolution of the line profile with a stick spectrum, which is defined as the sum of delta peaks at the position of the spectral line multiplied by the line's line strength. To store the stick spectrum on the computer, however, it must first be discretized in some way. And we can see this problem in the animation on the bottom right, where the red line represents an exact delta peak with some position u0, and that has to be somehow added to the discrete grid, which is indicated by the yellow bars. First, we find the grid index k of the grid point immediately to the left of the peak. And with that, we can also calculate the grid alignment, which is a number between 0 and 1 that tells us where exactly between the 2 grid points the spectral line is. And by setting the weights of these bins to the same value as the grid alignment, we can effectively distribute the delta peak over the 2 nearest neighbor bins. Now, in principle, we could group all lines together that have the same Lorentzian width and Gaussian width and use this convolution method to calculate the spectrum, and then repeat that procedure for all pairs of Lorentzian and Gaussian widths in the line list. But there could be thousands of those pairs of Lorentzian and Gaussian widths, so this is definitely not going to be a very efficient way to process the lines. Instead, it's more helpful to have another look at the equations and extend them to allow for varying line profiles. For the constant line shape, we had to generate a stick spectrum and convolve it with the line shape. This could be generalized by multiplying the stick spectrum with Dirac deltas for the Gaussian and Lorentzian widths. We call the resulting function the line shape distribution function, and this is now a function of the Gaussian and Lorentzian width axis in addition to the spectral axis. The line shape distribution function can be thought of as a 3D space that is only non-zero at those coordinates where there is a spectral line with exactly that line position and line width. I find it useful to compare this with stars in the universe, which can be considered as points in a 3D space, each with their own intensity. To obtain the output spectrum, the line shape distribution function must now be convolved with the line shape and integrated over the two width axes. Like before, we need a discrete version to use this in a program. The integrals can be replaced by sums, but like before, we must now account for the direct deltas in 3D space. Instead of having two nearest neighbors, in 3D space each spectral line has 2 times 2 times 2 is 8 nearest neighbors, over which the line strength should be distributed. Finally, before we move on, so far I've talked about 3D space because the Voigt profile takes 3 input parameters. In principle, this approach can be used for advanced profiles with more than 3 parameters as well, in which case the line shape distribution function will be higher dimensional. Since the new method requires to take the sum over 3 distinct axes, it can only be efficient if the grid size of the two width grids remains small. In other words, we need to find out how well a line shape of arbitrary width can be approximated by the weighted sum of two line shapes with discrete widths. To do this, we plot an exact Gaussian line shape in the plot on the right, depicted by the dashed black curve. Then we plot 5 line shapes with a discrete width in gray, each having a width that differs by 20%. The approximated line shape is the colored solid line, which is a weighted sum of the two nearest neighbors' line shape, also shown colored. As we vary the width of the exact line shape, we see that the approximated line shape very closely matches the exact line shape regardless of its width. Because the grid spacing of 20% is relatively coarse, this means that the number of grid points in the Gaussian width axis can be very small. For a Lorentzian line shape, we find a similar result. As many of you will know, convolutions can be calculated efficiently as a product in Fourier space. Typically, this means we need to perform 2 forward FTs and 1 reverse for each convolution. In this case, however, we can first apply the summations over the two width axes and only apply the reverse transformation once. Moreover, since the Fourier transform of the line shape is known exactly, we can use the algebraic form and don't need to do a numeric transform. This means that the total number of Fourier transforms is the Gaussian grid size times the Lorentzian grid size plus 1. One major benefit of defining the Voigt function in Fourier space is that we can use an exact function and thus do not have to rely on an approximation to the Voigt profile. The application of the Fourier transform in this way has implications for both the performance and the accuracy. Recall that the computation time of the conventional method scales with the number of lines times the number of spectral points. The new method scales with the number of lines plus NGNL plus 1 times n log n. This means that the new method can be bottlenecked by either the population of the line shape distribution function or by the convolution step. When it is bottlenecked by the convolution step, the number of lines in the spectrum can be increased without noticeably increasing the computation time. In terms of accuracy, our line profile is not quite an exact Voigt profile. Rather, it's a Voigt profile approximated by the weighted sum of 8 exact Voigt profiles. This means that by decreasing the step size of the width grids, the exact Voigt profile can be approximated with arbitrary accuracy. In the plot on the right, we show the root mean square error with respect to an exact Voigt profile for a number of Voigt approximations, including the popular Whiting approximation. On the x-axis is the relative contribution of Gaussian and Lorentzian functions to the Voigt function, with the far left being pure Gaussian and the far right being pure Lorentzian. As can be seen, for a Gaussian step size of 14% and a Lorentzian step size of 20%, our new method better approaches an exact Voigt profile for almost any combination of Gaussian and Lorentzian widths. Now that we understand the details of the spectral synthesis approach, it's time to compare it to the conventional synthesis method. We chose the open source code RADIS as the basis of our benchmarks because it already implements a number of optimizations. We implemented the new method in RADIS and compared it with RADIS's old synthesis method. The graph on the right shows the computation time for a CO2 absorption spectrum with varying number of spectral lines included. The computation time with the old method increases pretty much linearly with the number of included lines, as was expected. For a small number of lines, below 1000, the old method outperforms the new approach due to the convolution step being the bottleneck. For more than 1000 or so lines, the computation time for the new method remains essentially flat, with the computation time only increasing at about 1 million lines. At 1.8 million lines, the computation time of the new method is only 3.8 seconds, which is about 2.5 orders smaller than that of the old method. When comparing the accuracy of the two spectra, shown in the mid-bottom and zoomed in on the right, we see that the two methods reproduce the same spectra well within a 1% error. As mentioned earlier, it would be possible to improve the performance of the old method by truncating line shapes, but this would introduce significant errors from the two spectra. The real power of the new synthesis method becomes apparent when we look at parallel computation, such as on the GPU. For spectra with a large number of lines, in excess of 100 million, populating the line shape distribution function is the limiting step. Because only data of the line that is currently processed is needed, this step can be very easily parallelized. We used an experimental GPU implementation of our method to synthesize a CO2 absorption spectrum with the CDSD 4000 database, selecting up to 250 million lines. Computation time is limited by the CPU to GPU transfer rate of the database, which is only needed for the first spectrum and is shown in black in the right graph. For subsequent spectra, the computation time is only 50 milliseconds when including less than 10 million lines and becomes 110 milliseconds for 250 million lines. When expressing this performance as the number of lines times spectral points per second, this corresponds to a performance increase of about 5 orders of magnitude. The resulting spectra are shown in the graph in the bottom for temperatures between 300 and 4000 K, showing that the computation time is independent on the temperature of the spectrum. To conclude, we have shown that accurate high-temperature spectra require a large number of spectral lines, which, when using conventional spectral approaches, significantly increases computation time. Discretizing line widths and distributing the lines allows for an integral transform approach that is fast and accurate. For a typical spectrum, performance increase of 2 to 3 orders for CPU and 5 orders for GPU are achievable. And finally, perhaps most important of all, this is not some exotic code that only applies to a few select cases. It is a generic method that is easy to implement. The entire code for the CPU version is displayed on the right here. You can get it by downloading the code from my GitHub or by downloading RADIS. In addition, we are hoping to get it included in the new upcoming Hytran API. And with that, I want to thank you for your attention, and I look forward to your questions during the conference.